particular video, I'll help you figure out a couple different problems involving density and volume and radius and stuff like that. Here it says an irregular shaped chunk of concrete has a hollow spherical cavity inside. It says the mass of the chunk of concrete itself is 33 kilograms. It says the volume enclosed by the outside surface of this chunk of concrete is 0.025 meters cubed. And it wants us to find the radius of the spherical cavity in units of meters. Okay, so it's important to kind of store that information here. On the bottom left here, I gave you a visual. This is just some sort of concrete slab with a spherical cavity, or just an air pocket here that's in the shape of a sphere. All right. So the mass of the chunk of concrete is given as 33 kilograms. So this whole entire thing here that I'm circling back and forth with the air pocket inside has a total mass of 33 kilograms. And it says the total volume is 0.025 meters cubed. I know 0.025 meters cubed given is the total volume because it says enclosed by the outside surface. So this whole entire cube has a volume of 0.025 meters cubed. Okay. All right. And it wants us to find the radius. So to do that, well, let's go and crack it up. I'm just going to go ahead and start with the volume statement here. The total volume is going to equal to the volume of the actual concrete plus the volume of the empty pocket. Okay. So the blue sphere here in the diagram, that's just air. And then everything around it, as you can see, it will visualize, it needs to be concrete. Okay. So the 33 kilogram is just surrounding this air pocket, but the volume is given as total 0.025 meters cubed. So to find the volume of the concrete, right? So the volume given is not just the volume of the concrete, that's just the volume of the whole irregular shape with the air pocket. So we need to figure out what the volume of the concrete is. Well, to figure out what the volume of the concrete is, I know that density of the concrete equals mass of the concrete divided by the volume of the concrete. Okay. Well, to find V of the concrete, I would just manipulate this function to by multiplying both sides by V and moving density or rho down to the bottom right. Or again, multiply both sides by V at the same time divide both sides by rho. So the volume of this concrete that's inside the shape is mass divided by density. Well, the mass of the chunk of concrete is given to us as 33 kilograms, but I don't know what the density of concrete is. But concrete is a common value that you can find in these chart in the textbook. The density of concrete in grams per meters cubed. So you notice here in this chart that I've given you has units in grams per meters cubed. Again, it can vary between 2200 2500, but this chart here tells us 2.3 grams per meters cubed. So I'm just going to use the value given in this particular chart. If you happen to use a different value for concrete, that's fine too. Okay, again, it falls between like a range of about 2.2 to 2.5 grams per centimeters cubed. So on that, I'm just going to use the value that I have in this particular chart for this video, which is 2.37. So here, the mass of the slab of concrete is 33 kilograms. The density that I'm using here in this chart is 2.37 grams per meters cubed. So right away, I notice there's a discrepancy here. The unit on top is kilogram. The unit on the bottom here is in grams. But the question wants us to find the radius in meters. So notice here, the density value that I'm using in this chart is grams per centimeters cubed. So all you have to do is convert 2.37 grams per centimeters cubed to 2 kilograms per meters cubed. So quick conversion, for every 1 gram, for every 1,000 grams, that's 1 kilogram. So the conversion factor between grams and kilogram is that for every 1,000 grams, there's 1 kilo. And then for centimeters cubed, this one's a little tricky, so hopefully you're listening carefully. For every 1 meter, there are 100 centimeters. But this is cube, so if you do 100 cube, you'll get 10 to the 6th power. And that's where this 10 to the 6th came from. Once again, for every 1 meter, there's 100 centimeters. But it's centimeters cubed, so you have to cube the 100. Cube in the 100 will give you 6 zeros, so it'd be 10 to the 6th. So if you do that correctly, you'll get about 2,370 kilograms per meters cubed. Okay, so the only thing different here is that I left the mass in kilograms, and I converted the unit for density for concrete from 2.37 grams per centimeters cubed to kilograms per meters cubed. Hopefully you didn't get lost there. All right, on that, notice I have kilograms on top, kilograms on the bottom, And my volume here is in units of meters cubed, which is what I need because the question asks for the radius in meters anyways. So if you simplify that on your calculator, the volume of just the concrete, right? The volume of concrete outside this spherical shell, right? So you have to visualize pouring concrete outside of like a hollow basketball or something. So the mass on the outside is 33 kilograms, and that occupies a volume of 0.01392 meters cubed. So I know what the volume of concrete is, okay? Well, I can find the volume of the cavity, the spherical cavity. I know the total volume is given as 0.025 meters cubed. I just found the volume of the concrete surrounding that air pocket. So therefore, I can find the volume of the air pocket simply just subtracting both sides by the volume that I just calculated for the concrete, which is 0.01392. So if you do that correctly, you'll get that the volume of the cavity is about 0.0111 meters cubed. Now that I have the volume of the cavity, I can find the radius of the cavity because the cavity is here in this case, it says spherical, so I'll just set the volume of the cavity equal to the function for a spherical shape. The volume of a spherical shape is 4/3 pi r cubed. Well, here we're trying to solve for r, so I know the volume of the cavity because I just found it. So I'm just gonna go ahead and plug in the volume cavity from what I just got, 0.0111 meters cubed. 4/3 gets carried down, pi gets carried down, and this r cubed. So to get r cubed by itself, I need to multiply both sides by 3, and then divide both sides by 4 and pi. So hopefully you can keep up there. If you do that correctly on your calculator, you should get 0.0265 meters cubed. And you know here, this is r cubed. So to get r by itself, go ahead and just take the cube root of that, or raise the left side to the 1/3 power. And then if you do that on a calculator, you should get a value of 0.0138 meters, and that is our answer for this particular problem. Okay, it's a little tricky, so you just have to think a little bit. All right, let's do this next one. Here's a multiple choice one. It says a sample of oil in a cylindrical container is placed on a mass balance. It says the cylinder has a mass of 125 grams. So just the cylinder itself, empty cylinder, has a mass of 125 grams, and the cylinder itself has a radius of 4.2 centimeters. Okay, and it says there's a bubble of radius 3 centimeters midway up. Okay, so I just gave you a visual here to help you visualize. There's oil and there's a bubble. Not drawn a scale, of course, because the radius of the cylinder is 4.3 centimeters, and the bubble has a radius of 3, which is way bigger than this. But this is just to help you realize that there's a bubble in the center. And it says the reading on the balance is 1 kilogram, and the oil fills the measuring cylinder to a height of 25 centimeters. So by the time you put the cylinder, and you pour the oil on it, the scale itself reads 1 kilogram, and you fill this particular oil to a height of 25 centimeters. And it says which of the following is the most nearly density of the oil. So let's go ahead and crack it out. To find the density of the oil, you need the mass of the oil divided by the volume of the oil. Okay, well, I don't know what the mass of the oil is, nor do I know what the volume of the oil is, but I can figure this out real quick. We know that the total mass is equal to the mass of the oil plus the mass of the cylinder, right? The problem said that when you fill up the cylinder to a height of 25 centimeters, and you put that on the scale, it reads 1 kilogram. Well, the mass of the cylinder by itself without the oil is given as 125 grams. So right away I noticed there's a discrepancy between units, right? The mass of the cylinder is given in grams, but then the mass of the scale is given or the reading of the scale is given in kilograms. So keep that in mind as you practice. Make sure you convert units properly as you proceed with your work, okay? So I'm just going to go ahead and use the total mass as 1 kilogram, and then I'm going to set that equal to the mass of the oil. But you notice here, I plugged in 0.125 kilogram for the mass cylinder. So I convert 125 grams to kilograms, simply taking grams and dividing that by 1,000. Okay, so again, write out your units if you're a little iffy. So here, to find the mass of the oil, I can just subtract both sides by 0.125 kilograms. So 1 minus 0.125 kilogram will yield a value of 0.875 kilogram for the mass of the oil. So this is how much oil is in the cylinder, right? Now that you know the mass of the oil, well, you're halfway done. To find the density of the oil, you need the mass of the oil, which I just did. Now, I need the volume of the oil. So let's go and find volume. The problem sets that you fill this particular cylinder up to 25 centimeters. Okay, I don't know what the volume of the oil is because this air pocket is just trapped inside the oil, but it does occupy a volume, right? It's just empty volume. But okay, so the volume, excuse me, it's getting late. The volume of a cylinder is pi r squared times the height. And then here I kept the volume of the oil as unknown because in my work I need V oil, right? And I know the volume of the bubble I can just treat as a sphere. Okay, it is an air bubble. So I'll do that 4/3 pi r cubed. Well, here on the left side, pi is a constant. I know the radius is given, so I know the height is given. Okay, and likewise on the right side, the air bubble here, it says that it has a radius of 3 centimeters. So keep in mind these two r's are not the same. One is for the total volume for the cylinder. The r on the right side here is for the bubble itself. So I'm just going to go ahead and manipulate this function. To find V oil, I'm going to go ahead and subtract both sides by 4/3 pi r cubed. Once again, r here being the radius of the bubble. So I'm just going to go ahead and plug values in. So pi gets carried down. The radius of the cylinder is given as 4.2 centimeters. But once again, I want to convert everything to meters. So 4.2 centimeters is 0.042. So just divide that by 100. And that's where this value came from, 0.042. And this is now in units meters. And don't forget to square that. And then the height of the oil here, it reached a height of 25 meters. Or excuse me, 0.25 meters. And then the second term here is 4/3 pi r. What is it? 4/3 pi r cubed, because it's now volume. Okay. So this is a sphere. So the volume, the volume of a sphere. Man, I'm struggling right now. The volume of a sphere is 4/3 pi r cubed. The radius of the bubble is given once again as 3 centimeters, and I convert 3 centimeters to meters. And if you simplify this all in your calculator, hopefully I'm not goofing here because it's getting late. 0.00127 meters cubed. Now that I have the volume of the oil, the air bubble inside this oil, I already have mass. I just found V. So mass is 0.875 kilograms. The volume I found just now is 0.00127 meters cubed. And if I simplify that on my calculator, I'll get a value of about 689 kilograms per meters cubed. And the question here says most nearly. So 689 resembles 700. So I'm just going to go with choice B. That would be my answer. I hope that helps in terms of just kind of learning how to attack these different types of problem. All right, stay nerdy, don't be whack.